In the last video, we described how a linear feedback shift register could be used to generate a long sequence of seemingly random bits. In this video, we're going to code that. Although my videos on linear feedback shift registers have focused mostly on how to implement them in hardware, let's take a moment to simulate one in software. I'm sure there are better ways to do this than what I'm going to show you on the board here, but the idea is to get a better understanding of linear feedback shift registers by seeing what they look like in software. Now remember, I'm going to be explaining the code throughout this process, but it would be helpful if you understood things like constants and data types and loops and functions, and in fact specifically in JavaScript, because that's what I'm going to be using. Now be forewarned, my coding may look a little odd at times because I'm trying to force it into this narrow space, but in general I'm going to try and follow the guidelines of good coding conventions whenever it comes to JavaScript. Now, if you remember, in general, whenever we're looking at a linear feedback shift register, we have a sequence of these single-bit memory cells that the last output, in fact, this is where our bit stream is going to be coming from. All right. And that output is going to be going into this linear function along with the taps of some of the intermediate bits. So a couple of these intermediate bits we're going to be tapping off of. And then the result of that linear function is going to be the input into our shift register. So we've got a number of bits here. That's going to be changing. I'll show you how we're going to do that in code. And then every clock pulse, we are going to get all the bits in these single bit memory cells to move one position to the right. But the taps that were picked off of before are going to go into this linear function, which is an exclusive OR circuit, to generate the input into this leftmost bit here. Now, the exclusive OR, one of the things that we need to remember about the exclusive OR is that really, if you're looking at a bunch of inputs, and we are, there's a bunch of places that are being tapped off of here, the exclusive OR function really acts as a parity checker or a parity generator. It's going to be counting the number of ones, and if there's an odd number of ones from all these taps, it's going to be sending a 1 through here. If there's an even number of ones coming in from those taps, it's going to be sending a 0 here. So whenever we implement this in code, we're actually going to be simply looking at these taps and counting the number of ones. If it's odd, then we output a 1. If it's even, we output a 0. First of all, we're going to need to have the contents of this shift register. And those contents we're going to refer to as the state. So the state is going to be, depending on the number of bits, that is going to equal our, well, it's just going to be an integer, right? Then the feedback function is going to be a function. So the linear feedback function, that's going to be a function. And it is going to return either a 1 or a 0. It's going to receive as its inputs, and we'll talk about how we're going to receive those inputs. We're going to receive as our inputs a pattern of 1s and 0s representing the taps, and we are going to generate a single bit to be returned whenever we call this linear feedback function. When it comes to shifting, so shifting the state, we're going to do that with a bitwise operation that is 2 greater than symbols, and then the position right here, this number right here, identifies the number of positions that we're shifting. So every time we do a shift, all we're going to do is take our state and perform this operation on it. It'll shift it one bit at a time. And then the output, well, that is just going to be the least significant bit of the state. And so when we look at that bit, how do we grab that bit? Well, the way we grab that bit is by using something called a bitwise operation. And if you're unfamiliar with bitwise operations, this is a very important skill to understand, bitwise operations. And it's the ability to use a logical and, or, exclusive or, and inverse on an integer in order to just isolate or change or modify certain bits in our number. we're going to start out with this blank HTML file. Notice this begin and end script tags. That's where our JavaScript is going to go. Very first thing I'm going to do is I'm going to simply paste in some constants. Now understand that these constants, the purpose of these constants is to identify where we're going to tap off of our linear feedback shift register. So the shift register, each one of the bit positions represents a bit position in our state. And so starting at the least significant bit, remember the least significant bit is always going to be included. And so you notice that the least significant bit for every single one of these constants, the least significant bit is set to 1 because we're going to always include that. But there are also ones in other positions. Those ones in the other positions, those are going to identify the other taps, the other bits that are going to be tapped into this exclusive OR function. Now the next thing I'm going to do is I'm going to create a constant called tap mask. Now tap mask, the whole purpose of tap mask is to figure out which one of those constants I've selected. So it's just simply going to say I'm equal to this one. And this allows us to pick 8-bit, 6-bit, 5-bit, 4-bit, whatever it is. I'm going to go ahead and use tap mask 8. Now notice that they're 8-bit, and notice also that there are, for example, with 8-bit, there's also an alternate. And with all of these, there are really different ways that you could tap off, but each one of those masks will give us one of the progressions through all the 2 to the n minus 1 possible states that are going in that state register. Now I also need to identify to the program the number of bits. So I'm going to simply say number of bits. And we're going to set this to 8. Now, I realize there's a more graceful way to do this, but I just want to show you that in the program, we're going to need to know the number of bits and we're going to need to know the tap mask. We're defining those as constants right up front. The next thing what we're going to do is we're going to define a constant called register max. So we've got const, call this register max. Now let me talk a little bit about what register max is going to do for us. Register max is going to show the value, the largest value that can be contained in our state registers, and that shift register. Because number one, we need to know what the limit of the number of bits. We're defining this as an integer. We're going to use it as an integer, which means that there could be bits that are set in the wrong place, and we need to clear those out. I'll show you how to do that with a bitwise operation in a minute. The second thing register max is going to be doing is, well, it's equal to 2 to the n minus 1, which is, if you recall, the maximum size of a loop for our linear shift register if we've set our taps correctly. So I'm going to set this equal to math.pow 2 raised to the number of bits, all right, minus 1. Remember, that's 2 to the n minus 1. We've got that expression which represents the maximum size of our loop, 2 to the n minus 1. So that's all that function does. But that's not the only constant that I'm going to create in order to control our loop here. So we're also going to create a constant called the start seed. Now the start seed, well, I could actually just initialize my state to this starting seed, but I'm going to create a constant for it. It's not going to make the code any more efficient. It's just going to make it more readable, we hope. So the start seed, and what I'm going to do is create a start seed that is a 1 in the most significant bit position, zeros, and then end with a 0. End with a 1. Now the purpose of this start seed is to make it so that we don't start with all zeros, because if you remember, if you start with all zeros, or if all zeros ever gets into that shift register, we're going to stay at all zeros because of our linear feedback function, which is based on all exclusive ORs. So we want to make sure that we don't start with all zeros in that position. So I'm just going to come up with a basic value. I'm going to just have a 1, all zeros followed by a 1. In order to calculate that, we're going to do math.pow 2 once again, except this time it's going to be to the number of bits minus 1 plus 1. All right? And that's going to give us a 1 in the first position, all zeros, and then a 1 in the last position. Just a constant, once again, to make our code a little bit more readable. Now, let's start coding. The very first thing I'm going to do is I'm going to create a variable. And let's scroll down a little bit here. We're going to create a variable. We're going to call it state. This is our integer. This is what our shift register is going to be. And we're going to set it equal to our start seed. All right. All right, now, next. The next thing we want to do is create our function, the one that's going to do calculate the bit that's going to be put in the most significant bit position of our shift register. So I'm going to call this I'm going to create a function. We'll call it linear function. It's going to contain the current state. It's going to require the current state. And it's also going to require the taps. So this function is going to look at the current value that's in our shift register, figure out the bits that are going to be pulled from that current state, exclusive OR them all together, and give you the result. Now remember, the exclusive OR is simply a odd even count of the number of ones. So for example, if I have a 2-bit exclusive OR, if it's a 0, 0, then there's an even number of ones. If it's a 1, 1, there's an even number of ones. Both of those cases we output a 0. If it's a 0, 1 or a 1, 0, there's an odd number of ones and we output a 1. That's kind of the traditional way that an exclusive OR, even with multiple inputs, works. You just simply, if there's an odd number of ones at the inputs of like a large exclusive OR, you output a 1. So what we're going to do is we're going to clear out all the bits that are not part of the taps. And then we're going to figure out or count the number of ones that exist in what's left. So in order to do that, the very first thing I'm going to do is I'm going to let tap values. So this is going to be the state with all of the bits that are not taps cleared. And we can do that with a bitwise and. A bitwise and with the taps is going to clear all the bits that are not part of the linear feedback function, clear them all to 0. Once we've done that, then we just simply have to count the number of ones that's in that tap values variable in order to know what to send back. So we've got let, and I'm going to call this just exclusive OR feedback equals 0. We're going to initialize it to 0. And then what we're going to do is for j equals 0. So I'm going to make a loop, and I'm going to count the number of bits. So we'll do number of bits. And then increment j. And get into our loop. So we're just going to loop through all number of bits positions of that state ANDed with taps. And our XOR feedback is going to be, well, what we're going to do is we're going to add the tap value, or the tap values, shifted right so that the position that we're looking at. So what I'm going to be doing is I'm going to be, let's say I've got this result of the taps ANDed with the state. And so what that means is everywhere that we were not tapping off of state, we're clearing those bits. So that means these ones, and possibly some of the zeros, were ones that were in the position where we had taps. And so first time I go through this loop, I'm not shifting this at all. But every time I go through the loop, I'm going to take that value and I'm going to clear all of those bits by ANDing it with a 1 only in this least significant bit position. So that will, doing a bitwise AND of this with 1 is going to clear all the bits except for that position. Then the next time I go through the loop, what I'm going to do is I'm going to shift this 1 position to the right, do the AND again, and that's going to isolate this bit. And then the second time through the loop, I'm going to shift it right twice, and I'm going to AND with this position to figure out whether there's a 1 or a 0 there. And so in the end, what this exclusive OR feedback should contain is a sum of the number of ones that I've got in that taps value. So we're going to do tap values shifted right by J, and then ANDed with 1. And that's going to clear everything out except for the least significant bit after the shift. Now, once we've done that, the last thing we need to do is return just whether or not that result, the sum of the ones, we're going to return whether that was an odd number or an even number. And if you remember, the least significant bit identifies whether it's an odd number or an even number. So we're going to return XOR feedback ANDed with 1. All right. And that's our function. That function should generate a 1 or a 0 based on the exclusive OR of all the taps. Now, once we've done this, what we're going to do is we are going to loop the shift register, the state. So we're going to loop the shift register through 2 to the n minus 1 positions or states or conditions. All right. So we need to do a for loop, another for loop. This time we're going to use I equals 0. I is less than register max. Now remember, register max is equal to 2 to the n minus 1. And if we have our taps set correctly, what we're going to do is we are going to go through all 2 to the n minus 1 possible conditions. And then we're going to go I plus plus, and that will take care of our loop. Now, the very first thing I want to do is I just want to go ahead and output the current value that is in that, in that register. And so I'm going to do two things. First of all, I'm going to output the least significant bit. And that least significant bit is going to be our sequence of pseudo random numbers. But I'm also going to output the whole register so that we can take a look at the contents of our state. So I'm going to do two things. So we'll do document.write and state ANDed with 1. And that state ANDed with 1 is going to do the same thing that it did in the feedback function. It's going to strip out or clear all of the bits that come to the right of the, or come to the left of that, and output just a 1 or a 0 as that least significant bit. Then I'm going to output a colon to separate us from the rest of the output, and then we'll do state to string base 2. And then I'm also going to do this, I'm going to use this function called pad start, and that's going to put leading zeros to make it so that I can have a fixed number of bits there. The fixed number of bits is going to be the size of our register. Note that if I had leading zeros, those would be cut out if I didn't use this pad start. So I'm going to use pad start. In fact, let's do this on the next line so that I've got room. Pad start number of bits, and I'm going to pad that with a 0. And then I'm going to, because we're outputting this in HTML, I need to output my break to make it so that it shows up on the next line. All right, let's give ourselves some more room here. All right, now what comes next? Well, what comes next is doing the shift and setting it up for the next loop and next iteration. So all we've done at this point is output our current values. So I'm going to do state and bitwise and with register max. What's this going to do? Well, once again, our register max, if our register is 4 bits, then our register max is going to be 1111. And when I do a bitwise and, it's going to clear out anything that might have accidentally been brought in a previous operation. It's just going to fix us to make sure that we've got the correct number of bits there. Then what I need to do is OR this with, and a bitwise OR, what it's going to do is whatever I do a bitwise OR with, it's going to add that one. It's going to set that one for that particular bit position. And what I need is to bring in the most significant bit for the shift register. So what I'm going to do is linear function state, because remember, linear function took two parameters. It took the current state and it took the taps. So current state plus tap mask ended with 1. And that's going to make sure that just in case something got screwed up in linear function, we don't actually accidentally add ones that are not supposed to be there. Then shifted by the number of bits. So let me try and explain this. What we're going to do is linear function is going to come back with a 1 or a 0. But that 1 or a 0, what I need to do is I need to move it to the left by the number of bits. And then what can happen is that 1 would be moved over here, and then the register or the state will be here. And when I do a bitwise OR, I've moved it by the number of bits, which means I've moved it past all the bits that are part of the state. There will be zeros here, so this is going to be filled with all zeros. And when I do a bitwise OR, that's going to take this 1 or 0 and it's going to insert it right before or at the left, just beyond the left most significant bit position of the register and state. Now all we need to do is move everything 1 bit position to the right so that it becomes our new register or our new state. So now that we've done this, now all I should need to do is do state shifted right by 1 position. That's the end of our loop, and that actually should be the end of our script. So let's go ahead and save this. And now you can see when we run it in a browser, what we get is 2 columns. The first column is the least significant bit of that shift register, the state, and that shows us our sequence of pseudo random 1s and 0s. On the right-hand side, that's not as important. That's actually not part of the system. What I'm looking at here is the internals to that state. In other words, what is currently in the whole shift register. But you'll notice that the least significant bit of what is in that shift register matches what is being output from the, that sequence of 1s and 0s. Now, the one thing I don't like about this code is that there's no way to check if we've looped prematurely. How might we do that? Well, one of the ways we might do it is keep track of all the possible patterns that we've already received. In other words, the values that have been in that shift register, and see if the value in the shift register, the new value in the shift register, matches any of the previous ones. Very inefficient. But there's no real check, no real mechanism here to make sure that we're not looping. Another thing that we could look for is to watch or record the pseudo-random numbers, the pseudo-random patterns of 1s and 0s that have been generated, and see if we start to see a pattern, if it starts to loop prematurely before that 2 to the n minus 1. That said, hopefully this piece of code, hopefully this little exercise gave you a better understanding of how to generate that sequence of pseudo-random 1s and 0s using a linear feedback shift register.